Hey everyone, so today's lesson is on gases. We are into a new chapter which just deals with the state of gases for a lot of our molecules, okay? So what we're going to be focusing on today is we're going to be focusing on how gases act, we're going to focus on ideal gases, and then we're going to do some calculations involving gases where we're going to have to do some conversions as well. So, what is that one thing I just said, which was ideal gases? What are they? Well, ideal gases are just kind of made up gases that we have given certain properties so we could do some calculations with them, right? It's kind of like simplifying things a little bit just so we have an idea of where we're going. Ideal gases don't actually exist. They are made up gases that fit a certain scenario. So, what are the characteristics of these made-up gases? Well, the main one is that they are small. All right, they are small, super tiny particles. The next thing is that they bounce off each other. Okay. Some gases are not small, some are large. Sometimes gases stick together, but in ideal terms, they're going to bounce off of each other all the time. They don't slow down. Usually, gases slow down after a while, right? When they bump into each other, they transfer a little bit of energy and they slow down. Not ideal gases, okay? They don't slow down unless we change their environment. And last but not least, they're always in motion. So, ideal gases are always going to be in motion, they're always going to be moving. In real life, real gases, they kind of slow down. Sometimes they really stop if it gets cold enough, or sometimes if they get hit the right way, they'll just kind of float there. Kind of like that John Travolta meme. But anyway, they will always be moving. They're super small. They don't stick together. Okay, they bounce off everything. That's an ideal gas. That allows us to do some really nice calculations, which we'll talk about later. Real gases are larger and stick together for the most part. But the thing that you have to worry about is that they are larger. Okay, so what does larger mean? That means higher molar masses. So, the heavier gases, the less ideal it is. So something like xenon, which has a really high molar mass, is going to be less ideal. Something like helium that's really small is going to be pretty ideal. It's going to move pretty quickly. Okay? And that's just because since gases are larger, they kind of move slower. It takes more energy to move them. A big gas like xenon isn't going to want to move around a lot. It's also going to be attracted to other xenons, like other big molecules with a large charge. Whereas something like helium that's really small is going to move around a lot quicker, going to be easier to pick up speed, and is going to bounce off of things and not want to stick together as much. All right? So let's go ahead and let's get into these calculations. So here are our gas laws. We have P1 V1 equals P2 V2. This is just relating initial pressure and volume to final pressure and volume. 2 is V1 over N1 equals V2 over N1, which just relates volume in moles. 3 is V1 over T1 equals V2 over T2, which relates volume and temperature. 4, P1 over T1 equals P2 over T2, which of course is pressure and temperature. And this last one is P1 V1 over T1 equals P2 V2 over T2, which equates pressure, volume, and temperature. You'll see how all these work here in just a little bit. But first, let's kind of talk about what these equations are doing. They're relating these characteristics here. So in our first one, we have P1 V1 equals P2 V2. So that's relating pressure and volume. So let's say we have a container here, and it's got a bunch of gas molecules floating around. Well, what creates the pressure in a container? Well, it's these molecules bouncing and hitting the edge of the container. A can of hairspray has a bunch of pressure because the gas molecules are bouncing around, hitting the edge of the container, creating a lot of force on the outside of that container. There's a ton of molecules in there. Okay, they pack them in there, they're bouncing in to the inside of that container. So imagine what would happen if we just decided to decrease the volume of this container. Say we cut it in half. Now, those molecules are really close together. They're going to bump into more of the edges of the container. So when we decreased volume, pressure is going to increase. So that's what this is going to say. We might have, like, say, an initial pressure of 2, an initial volume of 1. Well, if we decrease the volume to 0.5, then the pressure needs to increase to 4 to make them equal one another. That's what this equation is essentially saying. We decrease the volume, we increase the pressure. Same if we went the opposite direction, right? If we increase the volume greatly of the container, now these molecules have a lot of room to move around. They're not going to be bumping into the walls as much. They're going to have some time to travel, to enjoy their time going to the edge of the container, okay? So now that we have increased volume, our pressure is going to decrease. Those molecules are going to have more room to move around. They're not going to bump into the edge of the container as much. Let's think about volume and moles, right? Moles is just the amount of molecules in a container, right? So say I have a container and it can move around. So actually, let's not make this a box. Let's make this a balloon, right? And say it's got 2 moles of gas in there. Those moles are going to bump around and they're going to go ahead and they're going to bounce on the inside of that balloon and expand it to as far as it'll go that the atmospheric pressure is pushing back on it, right? A balloon just doesn't expand forever. It'll stop at some point because the atmosphere is pushing back on it. So we have volume and we have moles. Well, let's say that I just add 2 more moles of molecules, right? I breathed into the balloon and added more molecules to this balloon. Well, this thing is going to go ahead and it is going to get bigger. The best balloon you've ever seen. So it's going to get bigger. So that's what this is saying. It's saying as we increase moles, our volume is also going to increase. Same as if we got rid of some of them. Say we just went down to 1 mole of this balloon. So now this is the most pathetic balloon you've seen. It's the one at the end of the party that nobody wants. So now if we decrease moles, our volume will decrease as well. Same kind of relationship here with temperature, right? If you increase the temperature, the volume's going to increase as well, right? So again, say we have a balloon here. We have these 2 molecules, and it's kind of normal room temperature. They're just moving kind of slow, just bouncing into the container every now and then. But say we increase the temperature and we put a fire underneath this balloon so that it doesn't pop, but it heats it up. Those molecules are going to move a whole lot faster. They're going to have a lot more energy bumping into the edge of that balloon, and it is going to increase the volume. Same that if we didn't have a fire underneath of it, say we had a ice cube. Okay, it would slow down those molecules. They would not move as fast or bump into that balloon, and it would make it really, really small. Okay? Crappy balloon drawing, I know. We experience this mostly in the winter time when it gets cold. Our tires get flatter. That's because that cold air is making those air molecules in your tires move slower and deflating your tire. And then people go ahead and then in the springtime they fill it up with air, and then it goes ahead and it warms up, and then it explodes the tire. That happens every now and then. You don't really hear of it too often. But in the springtime, if your tires are flat, okay, don't fill it up too much, because if the weather warms up, it's going to speed up those molecules and it might overinflate your tire. Kind of the same thing here with pressure and temperature, right? If you increase the temperature on a container, the pressure is going to increase as well, right? You increase the speed of those molecules, eventually that container is going to get a lot of pressure, right? It's like if you throw a can of hairspray on a fire, right? You increase that temperature, eventually it's going to go boom. Okay, that's because that pressure on the inside of that container is getting way too high. Combined gas law, just kind of the same thing with temperature and pressure. It just relates them together. So keep that in mind when you're doing your calculations, right? Think about what's going to happen if I increase temperature, decrease volume, increase pressure, or change the amount of moles, and make sure that that's making sense with your answers. let's go ahead and let's get into some conversions here. All right, conversions. This is where dimensional analysis is coming into play, right? We need to have everything in the correct units. For pressure, that happens to be AT10, which is just atmosphere. Right now, you are feeling pretty much 1 atmosphere. If you're at sea level, you feel 1 atmosphere. As we go up, there's less atmosphere. As we go down below sea level, we feel more atmosphere. So the thing with atmosphere you got to know is that I will give you things not in just atmosphere, but in kilopascals. Well, 1 atmosphere equals 101.3 kilopascals, which equals 101,300 pascals. 1 ATM also equals 760 torr, which also equals 760 millimeters of mercury. I ran out of room there, but it's mmHg. Let's just go ahead and let's move it down a little bit. Okay, so these are all units of pressure, and we're going to have to know how to convert from kilopascals, pascals, torr, and millimeters of Hg to ATM, which we'll talk about in a little bit. The other conversion you'll have to do is you'll have to go from Kelvin to Celsius. Well, we should remember that Celsius plus 273 equals Kelvin. And then the other thing you'll have to know is that in liters for volume, I might not give you liters, I might give you milliliters. We'll just know that there's 1,000 milliliters in 1 liter. Let's do some examples here. Oh, one more thing. At STP, it's 1 ATM, 273 degrees Kelvin, and 22.4 liters. Okay, I'll say that every now and then. So just be aware that at STP, I mean 1 ATM, 273 Kelvin, and 22.4 liters. So, let's go ahead and let's do an example. Say I have 700 torr, and I want to go to ATM, right? And all my calculations, when I plug in pressure, it's got to be in atmospheres. So, I have 700 torr. I'm going to start with what I'm given. Multiplication dot fraction bar, right? Torr on bottom, T-O-R-R, or Torricelli, who was a scientist that dealt with pressure. And then atmosphere is what I want on top. And then we just put the conversion here, right? Well, for every 1 ATM, it equals 760 torr. So we'll just divide by 760. That's a real common one that you'll have a lot, is you'll divide by 760 most of the time. So if we take 700 divided by 760, we'll get 0.92 ATM. So that's a simple conversion that you will see with pressure. We just divide by 760. With all these, you just divide by the conversion. Alright, let's do another example. Say I have 50,000 pascals. Another guy who dealt with pressure. Okay, I want to go 50 pascals not equal to, I want to convert it to atmospheres. Start with what you're given. 50,000 pascals, multiplication dot fraction bar, pascals on bottom, ATM on top. Well, for every 1 atmosphere, it equals 101,300 pascals. So we'll take 50,000 divided by 101,300, and we'll get 0.49 ATM. So that's with pressure. So with pressure, just always divide by whatever the conversion is. So if I give you millimeters of Hg, divide by 760. If I give you kilopascals, divide by 101.3. If I give you pascals, divide by 101,300. Temperature's pretty easy, but let's do a couple of those. Let's just go from 30 degrees Celsius to Kelvin. Add 273, right? 30 plus 273 is 303. If it was 100 degrees Celsius, it'd be 373 degrees Kelvin. If I gave you negative 73 degrees Celsius, it'd be 200 degrees Kelvin. All right, I expect you to know that. And then the last one, let's do milliliters, right? Say I gave you 500 milliliters. I wanted you to go to liters. Well, You could divide by 1,000, but the easiest thing for me to do is just go 1, 2, 3, 0.5 liters. Right? If it's 10 milliliters, I go 1, 2, 3. That equals 0.01 liters. If I have 2,000 milliliters, I go 1, 2, 3. It equals 2 liters. So those are our conversions. So make sure you have that down. Let's go ahead now and let's actually get into our gas law calculations. So I have gone ahead and put the gas laws up over here to the left. I'm going to leave them up there. And I got my first example. A container of volume 5.2 liters has a pressure of 1.2 atm. If we wanted the pressure at 2 atm, what will be the new volume, or what will the new volume need to be? So let's figure out what we're dealing with here. Are we dealing with pressure, volume, temperature, or moles? Well, in the problem it says we got a volume, and here we got a pressure. So what is the only equation that deals with strictly just volume and pressure? This is volume and pressure, but it's got temperature. This is pressure, but it's got temperature, volume, temperature. Okay, up here, number 1. Pressure and volume. That's all that is in equation 1. So we're going to be using P1V1 equals P2V2. And what we're going to do is we're going to combine 2 of those pressures and volumes together, the 2 that go together, right? And they could go in P1V1 or P2V2, but usually I put them in P1 and V1. So let's look at this. What volume and pressure are going to go together? A container of volume 5.2 liters has a pressure of 1.2 atm. That's going to go together, right? The 5.2 liters of volume and the 1.2 atm of pressure. And then later we change the pressure to 2 atm, and that should affect our volume. So let's go ahead and let's plug in what we know. So our pressure initial was 1.2 atm, or you can just put 1.2, but I'm putting the units. Volume was 5.2 liters. Liters are the units for volume. And then remember, if we wanted the pressure at 2 atm, so now we want the pressure at 2, what will our new volume need to be? Again, let's think about this conceptually. I want to increase the pressure on the inside of that container. So would I have to increase the volume or decrease the volume? I would have to decrease the volume, right? If I push down and make the container smaller, there's going to be a lot more pressure now inside that container. Those molecules are going to be bouncing off the edges of the container a whole lot. But really all we have to do now is solve this to figure out what the new volume is going to be. So we got to get volume by itself, right? We got atm and liters together. Let's get volume by itself. So let's go ahead and divide by 2 atm. Not just on one side, but both sides. That way atm crosses out. And now we're just left with V2. And look at that, pressure cancels out, we're just left with volume. So I'm going to take 1.2 times 5.2. That gives me 6.24. And I'm going to divide by 2 here. And my new volume, or my V2, is now, where's it at? 3.12. 3.12 liters. Hey, that makes sense, right? I said I had to decrease the volume to get that new pressure. My initial volume was 5.2. My new volume is 3.12. So there is an example of our first type of problem. No need to change units, right? Because it was already in atm and liters. But let's try to look at one where we might actually have to change the units. Next example here. A ball at 25 degrees Celsius has a pressure of 2 atm. If we increase the temp to 30 degrees Celsius, what is the new pressure? Well, let's go ahead and let's figure out what equation we got to use first, right? So we're dealing with temperature and pressure, it seems, and that's it. So what equation only has temperature and pressure? Number 4. So we're going to be using P1 over T1 equals P2 over T2. Let's make sure our units are correct, right? 25 degrees Celsius. No, that's not going to work, right? We want it in Kelvin. But luckily, that's our easiest one. We just add 273 to it, right? So 25 Celsius plus 273 is 298 degrees Kelvin. And then we got this other one down here. Let's go ahead and change that to Kelvin as well, which is 30 plus 273, which is now 303 degrees Kelvin. So now, easy conversion. Now we just got to pair everything together. Let's see what pressure and temperature goes together. A ball at 25 degrees Celsius has a pressure of 2 atm. Those two are going to go together, right? The ball was at 25 degrees Celsius, now 298 Kelvin, and at 2 atm. So let's put that in our equation here. We got 2 atm, and we got a temperature of not 25 degrees Celsius, but 298 degrees Kelvin. And I'm going to go ahead, I'm going to get rid of the units just to try to simplify things for this problem. I know that's a huge no-no, and I agree, but let's try to simplify things as much as possible. We don't know pressure 2, but we do know that we increase the temperature to 303 degrees Kelvin. First of all, if we increase the temperature, do you think the pressure is going to decrease or increase? If I increase the temperature, I think the pressure is going to increase, right? If you put a can of hairspray on the fire, the molecules move a lot quicker and it increases the pressure in that container. And now we got to solve for this guy. All right, we got to make sure that we can solve for P2. Algebraically, if you are unsure what to do, your best friend with situations like this is just to cross multiply. So that means we'll take 2 times 303 and we'll take 298 times P2. 2 times 303 is 606. 298 times P2 is 298 P2. And now this should be pretty easily algebraically wise, right? We got to get P2 by itself. Well, to get P2 by itself, we just divide by 298. So 606 divided by 298, and you should get a P2 of 2.03, but make sure you have the right units, right? Pressure is measured in atm. Okay, so it did increase the pressure just a tiny bit though, not a whole lot. Let's go ahead, let's do another. Our next example, we have a 0.5 liter ball. It's filled with 5 grams of oxygen gas. If I want a 2 liter ball, how much gas would I have to add in grams? So this one's a little tricky. So I'm looking at this, I have volume for sure, right? I got that 0.5 liters, but I have 5 grams of oxygen gas. None of these are grams, right? Well, what can we always change grams to? Moles, right? And the only one with moles is number 2. So we're going to be using V1 over N1 equals V2 over N2. So first things first, we got to get that grams to moles, right? So we got 5 grams of oxygen gas. Remember, oxygen gas is diatomic, which means it is O2. You'll never see oxygen just on its own. So it's always O2. So we're going to divide by the molar mass of oxygen gas to get to moles, which is 32. So 5 divided by 32 is 0.156, essentially, moles of O2. So let's go ahead and let's pair together what we know. We have 0.5 liter ball that's filled with 5 grams of oxygen gas. So those are going to go together. The 5 grams came from that 0.156 moles, so we'll put those guys together. We got 0.5 for my volume 1, and my moles 1 is 0.156. Volume 2, we want to get it to a 2 liter ball, right? So now we got to figure out N2, how many moles total. Remember, that's moles total. So when it says how much gas would I have to add in grams, remember that's moles total. We're going to have to do a little deep thinking here, okay? But first of all, if we want a larger ball, are we going to have less moles or more moles? We're going to have more moles. We got to add moles to make it bigger, right? Fill up with more molecules. It'll make it a lot bigger ball. So ones like these, I like to cross multiply. N2 times 0.5 is just 0.5 N2. 2 times 0.156 is 3.312. Let me look by using my handy dandy calculator. I think I'm wrong. Yeah, well, I was right. 0.312. Okay, now this is much easier algebraically, right? We divide by 0.5, divide by 0.5. So we need an N2 of, just double that, right? 0.624. So we're going to need 0.624 moles of O2 total. That's all together. But we already started with 0.156 moles, right? Remember, this is moles final. Moles initial, moles final, and I want to know how many grams I have to add. So what we're going to do is, in order to go from 0.156 to get to 0.624, we got to figure out how many moles we added. So I'm going to take 0.624 minus 0.156, and that'll give me how many moles of oxygen gas I'm going to need, which is 0.468 moles of O2. So that's how many moles I'm going to have to add, right? Again, this was initial. 0.624 ended up being our final. I don't want the final amount of mass. I want how much I have to add in order to get to that final mass. So we did a little calculations. We have to add 0.468 moles of O2. To get that to mass or grams, we multiply by molar mass, which is 32. So 0.468 times 32. We're going to have to add 14.98 grams of O2. Okay, let's do one more. Last one. So a container of volume 3 liters, 5 degrees Celsius, and pressure 720 millimeters of mercury is heated to 10 degrees Celsius and decreased to a volume of 2 liters. What is the new pressure? So here we have a lot of things. We have volume, we have temperature, and we have pressure. Well, the only thing that deals with that is number 5, the combined gas law. Well, let's go ahead and see if we're in the right units. Volume seems to be good. We're at 3 liters. Temperature, 5 degrees Celsius. Nope. We got to add 273 to that. So add 273, that gives us a 278 degree Kelvin for that one. And then we also have a 10 degrees Celsius. So let's just go ahead and take that out of it as well and change that to Kelvin. Good. That's done. Well, we also have a 720 millimeters of mercury too. Crap. We got to get that to ATM. So what we're going to do is we're going to take 720 millimeters of mercury. And remember, for every 1 ATM, there's 760 millimeters of mercury. So just 720 divided by 760, which I don't know off the top of my head. 0.95. All right, so now we have everything in the correct units, and now we can start plugging and chugging. So we got to find a pressure, a volume, and a temperature together. Well, at the beginning, it was 3 liters, 5, and 720. So those go together. My initial pressure was my 720 millimeters of mg, which I've changed to 0.95. My initial volume is 3, and my initial temperature was 5 degrees Celsius, which I have now changed to 278. P2, that's what I'm looking for, right? It says, what is the new pressure? So I'm looking for P2. The new volume is 2 liters, and the new temperature was 10 degrees Celsius, which I changed to 280. Before we start cross-multiplying here, let's just go ahead and let's think about this, right? If I decrease the volume, right, I went from 3 to 2 liters. I decrease the volume, and I increase the temperature, so I'm speeding up those molecules on the inside as well. Is that going to increase the pressure or decrease the pressure? Should increase the pressure. I'm making it smaller, and I'm heating it up. So let's go ahead and let's see what happens here. So let's go ahead and cross-multiply. So I got 0.95 times 3 times 283. And then I got P2 times 2 times 278. I got to get P2 on its own, so I'm going to divide by 2 and 278 to both sides. Doing a weird squat there to get that written in. So now P2 is by itself, so 0.95 times 3 times 283 gives me 806.55. Divided by 2 times 278 gives me a final pressure of 1.45 ATM, which makes sense. Our initial pressure was 0.95, but now our final pressure is 1.45. That is our intro to gases. If you guys can get this down, get your conversions right, you're already got 50% of this chapter down. So go ahead, check out the practice. Let me know if you have any questions. Have yourselves a good day.